After serving an apprenticeship and working as a design engineer, Dr. Bob Allen served in the Royal Navy for 21 years with the final rank of Commander. On leaving the Navy, he joined Castrol Marine for 13 years as the technical manager. He then took up an academic career at Plymouth University as a lecturer and researcher. Now recently retired from lecturing, he is still involved in one research project. Bob has been active in the local joint branch, holding the posts of treasurer and twice as branch chairman. His talk brings together his recent research activities, backed up by over 35 years' experience in the marine industry.
My name is Robert Allen, and this talk is about the decarbonising shipping and reducing greenhouse gas emissions. This is a presentation which was done in May to the Joint Branch Devon and Cornwall RENA IMarEST. So I'll start now, and first of all I want to look at IMO and what they've set as a target, and look at some of the outputs, particularly from marine propulsion engines. So IMO set a target to reduce greenhouse emissions by 50% by 2050 or earlier, and this is from a baseline of the year 2008. Now, diesel engines propulsions accounts for some over 99% of commercial marine power. So if we look at a diesel engine, it's fed with air, which is made up of oxygen and nitrogen, fuel, and I've set 170 grams per kilowatt hour as a typical value, and about 3% sulphur for heavy fuel. And of course, a small amount of lube is consumed if it's a two-stroke engine in cylinder lubrication. The outputs of the engine are the exhaust gases. Some oxygen goes through, most of the nitrogen goes through. There's a certain amount of water vapour, but the greenhouse gases we're more interested in is carbon dioxide, sulphur oxides, nitrogen oxides, carbon monoxide and hydrocarbons. We could of course include water vapour in the H2O in the greenhouse gases, because it is actually a major greenhouse gas in its own right. But for the IMO, we just look at the CO2, NOx and SOx. So the principal greenhouse gases, as I said, are CO2, sulphur dioxide and nitrous oxides. And if we look at a typical greenhouse emissions from a marine hydrocarbon fuels, from the typical engine as we had before, then for every tonne of hydrocarbon fuel burnt, we get these various outputs. So for heavy fuel, we get 3,300 kilograms of CO2. Very low sulphur fuel oil, slightly less, 3,200 kilograms. Marine gas oil, 3,100. And liquid natural gas on a dual fuel burn is 2,900. And we get smaller proportions of sulphur oxides and nitrous oxides for each fuel. However, one thing to note is that the type of hydrocarbon fuel has limited effect on the carbon dioxide emissions. And the carbon dioxide emissions represent over 90% of all these three greenhouse emissions. Now, according to the International Maritime Organization, shipping emits some 940 million tonnes of carbon dioxide per year, and is responsible for some 2.5% of all greenhouse gas emissions. And without mitigations, emissions are projected to grow over the next 3 decades. So the IMO have an approach to reduce greenhouse emissions, and I've put these into 3 categories. The first one is to use less fuel, and these are done by efficiency indexes. The second one is to use low or zero carbon fuels. And the third one is to look at exhaust treatment technologies typically scrubbers and selective catalytic reduction systems. So if we look at indexes first, now the key to it is that the metric by which they measure any performance improvement is in grams of CO2 per tonne mile. So that's the metric for all the indexes that IMO propose or apply. And there are two basic indexes. One is the Efficiency Design Index, EEDI, and that's the performance of the hardware of the ship. And again, it's in grams per tonne mile. And the other one is the Energy Efficiency Operational Index, and it's how you actually operate the ship. So typically slow steaming, weather routing, etc., etc. And of course, the ship has to have a ship energy management plan. One thing to note that shipping vessels, because they have a very low cargo compared to the size of the ship, are not required to have an attained Energy Efficiency Design Index. So the IMO have actually set out limits for various ships based on capacity and deadweight against the grams of carbon dioxide per tonne mile. And they have increasing regulations. So Phase 0, Phase 1, Phase 2 and Phase 3. So for each year, each of these phases, there is an increase in the required design efficiency. For larger vessels, they're more efficient than smaller vessels, and the indexes allow for different types of ships. So it could be tankers, bulk carriers, container ships or general cargo ships. And vessels designed in 2025 are to be 30% more efficient than those designed in 2015. After 2025, further efficiencies gains become difficult. So a ship designed today, or for 2025, will be 30% more efficient than a ship designed in 2013. So what are the technologies employed to increase design efficiency? The first one is hull design, particularly aft, for improved propeller fuel flow. And that's the rudder design, the propeller design, hull painting, and even talks of air lubrication. And the idea is to reduce wave and hull friction resistance. So less power for the same speed. For the engine, there's waste heat recovery, engine propeller optimization, shaft generation, and perhaps a very small amount in engine efficiency. So they're reducing fuel usage. And of interest to some areas, but not really big, is a power augmentation, which could be rotors and sails, and maybe even the use of PVs and photovoltaics and batteries in harbour. And of course, cargo space optimization to actually get the maximum deadweight of the ship. So I'd like to move on to look at low, zero or carbon fuels. And I think we have to think about the energy for ships. And this is an important thing to consider because ships require stored energy to complete a voyage. Specific stored energy is measured in megajoules per kilogram, and that's the international standard. And the rate of energy use is in joules per second, which is in watts. All conventional ships obtain power from exothermic chemical reactions. This typically involves a reaction between a fuel containing hydrogen and carbon with oxygen. Different fuels have different values of specific energy quoted in megajoules per kilogram, and different fuels have different densities, hence volume of stored energy to be carried to complete a voyage, and it's measured in megajoules per metre cubed. And power requires conversion of the chemical reactions, and not all energy released is converted to power, and that's what's called thermal efficiency. Energy per kilogram and energy per metre cube is important when comparing different fuels and especially on pricing. So first of all, I'd like to look at the carbon content of marine hydrocarbon fuels. So hydrocarbon fuels are made up of 4 basic components. These are saturates, aromatics, resins and asphaltenes, and it's commonly referred to as SARA. Marine gas oil or diesel fuel, or similar to automotive diesel fuel, comprises of saturates and aromatics, and heavy fuels contain small percentages of resins and asphaltenes in addition to saturates and aromatics. The simplest hydrocarbon saturate is methane, CH4, which comprises 75% by weight of carbon. And the simplest hydrocarbon aromatic is benzene, C6H6, which comprises 92.3% by weight of carbon. So if we look at the reaction of carbon and oxygen, we see that carbon and oxygen react to form CO2. And if we do this by molecular weight, we see that 44 grams or 44 kilograms of carbon dioxide will come from the reaction of 12 kilograms of carbon. Hence, 1 kilogram of carbon will produce 3.67 kilograms of CO2. And if we look for methane, 1 kilogram of methane, and we take the 75% times 3.67, will give us 2.75 kilograms of CO2. And if we do the same exercise for benzene, 1 kilogram of benzene will produce 3.39 kilograms of carbon dioxide. Carbon fuel combustion, when the energy comes from the combustion of fuels, is quoted in megajoules per kilogram. The combustion of a hydrocarbon fuel comes from both the reaction of hydrogen with oxygen to produce water or steam, and the reaction of carbon with oxygen to produce CO2. So the combustion of methane can be expressed as CH4 plus 2CO gives us 2CO2 plus 2H2O. And we can break that down into the various components, one for the hydrogen and one for the carbon. The combustion energy of hydrogen is quoted at its lower heating value, LHV, is 120 megajoules per kilogram, and the combustion energy of carbon has a lower heating value of 32.8 megajoules per kilogram. So if we go back and look at methane, which is 75% by weight by hydrogen, 25% weight by hydrogen and 75% weight by carbon, the energy of combustion for 1 kilogram, and if we do the sums, we see that 0.25 times 120 plus 0.75 times 32.8 will realise 54.6 megajoules. If this method is used for more complex hydrocarbons, then at 78.5% carbon, equal energy is obtained from the carbon and the hydrogen. And what's to note is that all marine fuels have a carbon content greater than 78.5%. So removing the carbon results in a reduction in energy, which has to be compensated by additional hydrogen. So let's look at a comparison of typical fuels, and I've included carbon and low and zero carbon fuels. So I've looked at marine gas oil, liquid natural gas, liquid petroleum gas, ammonia and methanol. And we see that, first of all, I'd like to draw your attention to the lower heating values. So marine gas oil at 42.6. And if we look down at the low carbon fuels or the zero carbon fuels, and if we look at ammonia, it's 18.6. So basically ammonia has half the heating value or the energy value of marine gas oil. And this is replicated to some extent in the energy per metre cubed. Also, we have to consider how we're going to store this on board a ship. So marine gas oil will be in normal tanks, LNG is in pressurised tanks, LPG is in pressurised tanks, ammonia has to be in pressurised tanks, and it's basically the same as LPG, and methanol, which has a flash point of minus 11 degrees centigrade, has to be in enclosed tanks to stop an explosion. Gasoline and diesel fuel, that's automotive, contain approximately 86% weight by carbon, and they contain also 35% by weight of aromatics. In marine heavy fuel, these fuels can contain over 90% carbon with high aromatic content, with a density sometimes over 900 kilograms per metre cubed. If we look at fuel energy by volume, we see that marine gas oil has a lot of energy and the units for the volume are megajoules per metre cubed. And we can see as we come down to LPG and LNG, it's always been known that LNG, we need twice the volume to compete with MGO on an energy basis. And methanol and ammonia are quite low down. I've included liquid hydrogen. Remember that liquid hydrogen boils at minus 250 degrees centigrade. You can do the sums for pressurised gaseous hydrogen if you use the normal equation of state PV equals MRT, where R is equal to 4,124 joules per kilogram per degree Kelvin. Also to note that a megajoule is equivalent to 0.78 kilowatt hours. So let's have a look at zero low carbon fuels. Ammonia is NH3, one atom of hydrogen and 3 atoms of hydrogen as a marine fuel. It has zero carbon. It's been considered as a marine fuel for reduced greenhouse gas emissions. It contains 17.6% by weight of hydrogen, has a lower heating value which is quite low at 18.6, and by comparison marine gas oil has a lower heating value of 42.6 megajoules per kilogram. So the ratio is 2.3 to 1. All the classification societies have published guidelines on ammonia storage, and the main engine builders, MAN and Wärtsilä, are currently conducting full-size trials to introduce ammonia ready engines by 2024. These will likely be dual fuel engines. Ammonia is not highly inflammable, and concentrations in air as low as 0.25% can cause fatalities. Its storage as a liquid on board, similar to LPG. It's got quite a high flash point. Auto ignition 651. You have to be around 250 for a compression ignition engine. Explosive limits are quite high, and the density is 600 kilograms per metre cubed. So let's have a look at the combustion of ammonia in an internal combustion engine. Ammonia is difficult to ignite, burns colder, and has a lower flame speed. It requires a strong ignition source, which can be provided by a compression ignition pilot fuel. So compression ignition is diesel fuel in a diesel engine. So a small amount of diesel fuel is admitted. It ignites under the compression ignition, but before that, ammonia is added to the combustion chamber and will actually ignite the ammonia. And Wärtsilä have actually done some trials and reported successful power production with 30% ammonia, 30% marine gas oil and 70% ammonia. It's not sure what they mean by successful power production. Ammonia has roughly half the lower heating value of MGO. Hence an increase in fuel consumption is required to achieve a comparable combustion energy. Let's explain this by an example. The lower heating value of 1 kilogram of marine gas oil is 42.6 megajoules, and the lower heating value of 1 kilogram of ammonia is 18.6 megajoules. So taking 30% marine gas oil and 70% ammonia, and if we do the calculations, we come out that this mixture will produce 25.93 megajoules for 1 kilogram. So making a comparison with marine gas oil, we see that the ratio is 1.65. And what this means is that 65% increase in gravimetric fuel consumption for the same amount of power energy. However, we do get a reduction in CO2 emissions of 70%. So let's have a look at where we get ammonia from. Ammonia is produced in the Haber-Bosch process that combines hydrogen and nitrogen under pressure and temperature. Nitrogen is from the air by compression and liquefaction, hence we have liquid nitrogen around. And hydrogen is from 4 different processes. And they're given terminology in colours. So grey hydrogen is a steam reformation of methane. So steam and high pressure is mixed with methane, and it will release the hydrogen, but it will also release quite a large amounts of CO2. Blue hydrogen is the same as grey hydrogen, but there is a capture of the CO2 by filtration. Green hydrogen, there's a lot talked about green hydrogen. This is by electrolysis of water using renewable energy, and typically we can get 500 kilograms per day of hydrogen using 1.5 megawatts of renewable electrical power. And finally, in its infancy, is turquoise ammonia. This is direct pyrolysis of methane to hydrogen and solid carbon, and again using renewable energy. Just like to cover the idea of fuel costs. Current fuel estimates for the production of green ammonia is about $500 per tonne. Delivered as bunker fuel would increase this to around $750 per tonne. But at present very little green ammonia is produced and traded, hence the above prices are estimates. The current price for marine gas oil is in the range of about $1,400 per tonne, and the current global price for very low sulphur fuel oil is $1,130 per tonne. So what are the fuel cost implications? Voyage costs dominate the fleet total costs, and fuel costs represent between 60 and 70% of costs. So an example of typical fuel cost. Here's a scenario. So we have a vessel developing 10 megawatts of power from a 2-stroke engine with a rated specific fuel consumption of 165 grams per kilowatt hour on a hydrocarbon fuel. Let's assume 30% of the fuel savings from indices based on the year 2008. A further 30% reduction in carbon dioxide by dual fuel operation with 70% very low sulphur fuel oil and 30% green ammonia on an energy basis. So the total reduction of CO2 from the 2008 baseline is 51%. So at this stage we're actually under the 50% 2050 target set by IMO. However, let's look at the operating costs. So creating a spreadsheet, the black dotted line, that's the hourly cost of 10 megawatts of power on very low sulphur fuel oil. The black solid line is the hourly cost of 7 megawatts of power on very low sulphur fuel oil, and this is on a fixed price of very low sulphur fuel oil of $920 per tonne. These two lines would go up and down depending on the global bunker prices, but I've just, for this exercise, I've used $920 per tonne. The green line is the hourly cost of ammonia to provide 3 megawatts of power, and the red line is actually the green line added to the solid black line, which is the cumulative hourly cost to provide 10 megawatts of power. And the x-axis is the range of bunker prices for green and anhydrous ammonia. So we see on this fuel cost, the break-even point is that green ammonia at $400 per tonne bunkered. If it's at $600 per tonne, then we're adding some 25% to the operating costs of a ship burning ammonia. So what is the progress by engine designers for engines operating on low and zero carbon fuels? MAN Energy 2-stroke engines we have available for installation in 2024 and a retrofit package in 2025. They say it's likely to be dual fuel engines using existing fuel experience technology. So they have a lot of experience on dual fuel engines using a hydrocarbon fuel like marine gas oil or very low sulfur fuel oil and LNG. Similarly, Wärtsilä have similar experience, and the test results are very encouraging, with one test performing very well when running on a fuel with 70% ammonia content up a typical marine engine range. But we've seen that 70% ammonia can actually be very expensive. Wärtsilä anticipates having an engine concept with ammonia fuel in 2023. For MTU, they've generation of MTU series 2000 and 4000 engines for use with sustainable fuel synthetic diesel is available from 2023. This is called the Methanol Initiative, and possibly these engines will actually run on methanol. So let's have a look at ammonia for electrical fuel generation, and there's quite a lot of interest in this and development work, and this is for fuel cells. Fuel cells operate on hydrogen and are approximately 50% thermally efficient. So green ammonia is heated using fuel cell waste heat and passed over a catalyst to release both nitrogen and hydrogen. The hydrogen molecule is larger than the hydrogen molecule, and hydrogen is separated in a filter. And this vessel, the North Sea OS Viking Energy, North Sea offshore supply vessel, or Viking Energy, is being equipped with 2 megawatts of fuel cells, and the installation is next year, and it's operational expected in 2024. I'd like to point out that nothing is new. In 1943, Belgium, during the Second World War, could not find any diesel fuel or petrol to run their buses. So they developed a system operating on ammonia and coal gas mixture, and this was due to the shortage of liquid fuel. So they mounted high-pressure coal gas cylinders on top of the bus and 2 ammonia carriers on the front of the bus. And there's a very good paper which is down at the bottom, it's referenced at the bottom. You'll find it probably quite easily on the internet, which gives you a full description of the performance of these buses and the consumption of fuel. So nothing is new. So we've been running in internal combustion engines on ammonia mixtures. I'd now like to turn to the third item on the IMO list, which is basically scrubbing out greenhouse gases from exhaust emissions. So the greenhouse gases, sulfur dioxide, nitrous oxides and carbon dioxide, are acidic gases and will form acids with water. The first thing to look at is that sulfur dioxide is 50% more soluble in water than either carbon dioxide and nitrogen oxide. It can thus be readily neutralised by the buffering capacity of a calcium carbonate in seawater, So scrubbing with seawater will remove a lot of the sulfur dioxide. Oxides of nitrogen, NOx, can be neutralised in a reactor using urea, and that's selective catalytic reduction. Please note that NOx is 95% nitric oxide and 5% nitrogen dioxide. And carbon dioxide has very limited solubility in water, but can be neutralised using alkaline solutions of hydroxide ions. And I'll look at this in a bit more detail later on. So let's have a look at typical results of saltwater scrubbing with a heavy fuel. And this is a test result from a 4-stroke engine which was rated at 9,600 kilowatts, and it was operated at 76% of its maximum continuous rating with a specific fuel consumption of 187 grams per kilowatt hour. So the scrubbers took out virtually all of the sulfur dioxide, so there's a very small amount left. The saltwater scrubbers had very little impact on the NOx, and it had very little impact, if any, on the carbon dioxide. So scrubbing out greenhouse gases from exhaust emissions, I'd like to look at the SOx and the NOx. The scrubbers, seawater scrubbers, are quite large pieces of equipment built in the uptakes on the funnel areas of the ship. So you'll have a main engine exhaust, an auxiliary engine exhaust, and you'll have 2 scrubbers. So you can see at the bottom right hand corner the size of the man, and this gives you the relative size of the scrubber. If we look at the SCR for NOx, selective catalytic reduction using urea, we see there's a large mixing chamber which comes off the exhaust exhaust receiver. It passes into a reactor, so the urea reacts with the nitrogen oxide, and these gases then pass through the turbocharger and up to atmosphere. These are large installations when compared to the size of the engine. And if we go back to slide 3, remember that CO2 emissions represent over 90% of all greenhouse gas emissions. So we're employing these 2 very large installations for just 10% of the greenhouse gas emissions. So let's have a look at alkaline solutions for CO2 reductions. Alkalinity is a function of the hydroxide ion, which is designated as OH-, and it comes from the dissociation of water, which can be expressed as hydrogen plus OH-. Alkaline ions will react with CO2 to form stable carbonate ions and water, and the overall reaction is CO2 plus 2 OH-, or OH- plus OH-, 2 OH-, will give us CO3 H2O. So 44 kilograms of CO2 requires 34 kilograms of hydroxide ions for complete reduction. An alkaline water can also react with sulfur oxides and nitrous oxides. And note that closed-loop scrubbers for sulfur oxide use fresh water and sodium hydroxide, produce an alkaline solution for SOx reductions. So current methods for reduction of hydroxide ion solutions are used in carbon dioxide capture, and this capture is for industrial purposes at the moment. So the chemical methods, we can use substances like monoethanol amine or other amines, and this has a pH of 11.8 at a certain type of aqueous solution. It's quite expensive, $1,350 a ton. Sodium hydroxide, a pH of, again with 0.1 neutral alkaline solution, slightly higher at 13 pH, much cheaper at $350 to $600 a tonne, depending in the world where you embark it. And also we can produce alkaline water or hydroxide ion solutions by water electrolysis. So the quoted figure for hydrogen production is 1.5 megawatts for 20 kilograms per hour of hydrogen. 20 kilograms of hydrogen will also generate, theoretically, 340 kilograms of hydroxide ions. However, if the 1.5 megawatts of power is generated on board a diesel engine with a fuel consumption of 200 grams per kilowatt hour, then the hour of fuel consumption is 300 kilograms of fuel, which will produce 900 kilograms of CO2. So 44 kilograms of CO2 requires 34 kilograms of hydroxide ions. Then 900 kilograms of CO2 requires 700 kilograms of hydroxide ions. Compare the 700 now with the 340 kilograms of hydroxide ions above, and we find that the net outcome is that on board electrolysis increases CO2 emissions, and that's even if the hydrogen produced is converted to electrical power, and also there's no hydroxide ions to treat the main engine exhaust. So looking at absorption capacity, 1 tonne of fuel, if we take 1 tonne of fuel, will produce 3 tonnes of CO2. Then sodium hydroxide, NaOH, so 44 kilograms of CO2 requires 80 kilograms of sodium hydroxide, and 3 tonnes of CO2 requires 5.45 tonnes of sodium hydroxide. So 1 tonne of fuel requires 5.45 tonnes of sodium hydroxide for complete neutralisation. Similarly for monoethanol amine, and the quoted figures are 500 grams of CO2 per kilogram of MEA, so 3 tonnes of CO2 requires 6 tonnes of MEA. And these are both the above are complete capture. So storage on board of large amounts of chemicals and spent chemicals is not practical. I'd now like to just consider a trial which was done some time ago, and it's a ship scrubber trials, and it was using alkaline water produced by electrolysis, and it was run by a company called EcoSpec in Singapore. And they used a 2-stage scrubber. First one, they used seawater to scrub out the sulfur oxides, and then they had alkaline water, and they got it up to 9.5 pH for the CO2 and the nitrous oxide. The company never published specific details on this trial, nor reported the alkaline water flow rate, how much hydrogen was emitted from electrolysis. But doing a quick calculation on a typical ship of this size and its voyage profile, I estimate the emissions were about 2.6 tonnes per hour. No further trials were conducted because there were serious system failures, and they got sued, and in fact the company went bankrupt. However, certain things did come out of the trial. So this was the Africa Max tanker, Coral Sea, and during the trial they found they could remove 92.9% of NOx removals, 82.2 NOx removals, and a significantly 74.4 carbon dioxide removals. And these were measured by the American Bureau of Shipping. This one-off trial showed that scrubbing water with water with a pH 9.5 can reduce levels of CO2, can reduce greenhouse gas emissions. And the system failed because of two things. One was the acidic wastewater discharge was lower than 7.5 pH, i.e. it was getting into the very acid stage, and 7.5 pH is the IMO limit. And was seen before, using ship power for electrolysis to generate alkaline water is not economic or practical, it increases CO2 emissions. Also a failure. But the thing to take away from this trial is that it did show that alkaline water in a scrubber could reduce emissions. I'd like to just look at NOx emissions because there is indication that when ammonia is part of the fuel, more NOx is produced. And this is a reference from one of the papers. It says the major challenge with the use of ammonia as a fuel are lower heat flux and increased NOx emissions. And there are other typical papers which actually come up with similar conclusions. NOx is comprised of 95% nitric oxide and 5% nitrogen dioxide. Nitric oxide is relatively insoluble in water. However, it will oxidize to nitrogen dioxide in contact with air and is then relatively soluble in water. So NO2 in water produces nitric and nitrous acids, and the acids need to be neutralized by hydroxide ions. So we can rate out three types of equations here. One is the reaction of nitric oxide and nitrogen dioxide with hydroxide ions to create oxidation. The oxidation will then react with water to form acid, nitric acid and nitrous acid, which but before that the nitrogen dioxide can be reacted with hydroxide ions again to form a stable nitrate ion and water. So MAN and Wärtsilä are yet to publish the levels of NOx emissions from ongoing engine tests using ammonia. So I'm waiting for these test results to come out to see if there is an increase in NOx emissions. So looking at all these problems, there was a need identified for low-cost, high-volume production of alkaline water on board a ship and safe disposal of wash water into the sea. So a big ask. So 2 bullet points. One is the use of alkaline water for scrubbers has been tested. And second, what other methods can be used to produce high pH alkaline water? So looking around all the sort of research areas, one thing that stood out was that significant research work was undertaken in Japan on water purification and the properties of black tourmaline shoal. The tourmaline crystals possess permanent polarity and electrical charge. And there's a very good paper published, Tourmaline group crystals reaction with water, and there are several patents published which can be read about. The patents are quite easy to get hold of. The paper is a little bit more difficult. But the above of how these tourmaline crystals react with water is part of an ongoing investigation at Plymouth to determine the feasibility of this science. So these patents and the paper describe the performance of tourmaline crystals which possess permanent polarity and electrical charge. And these tourmaline crystals are combined with an electrically insulating material which insulates the fine crystalline crystals, tourmaline crystals, from one another. And the free bodies are preferably small ceramic spherical balls. And the claim is that when the ceramic balls come into contact in an aqueous solution or aqueous medium, the embedded crystals can also come into contact with each other. The crystal contact will generate small but intense electromagnetic field which can dissociate water. So lots of contacts, lots of hydroxide ions produced. There are also many other scientific papers describing the properties of tourmaline, and particular black tourmaline shoal. So what is tourmaline? Well, it's a naturally occurring crystalline boron silicon material. There are outcrops in Cornwall, and in China clay flits. It's often referred to as tourmaline chol. Tourmaline crystals possess the characteristics of an electret. Now, the definition of electret is the electrical equivalent of permanent magnets. They carry a permanent positive charge on one surface and a permanent negative charge on an opposite surface. As a lot of experimental data showed that the impact of tourmaline increases as the fineness and specific surface area of the tourmaline powder increases. So here's some picture of some 3.5 millimeter diameter ceramic tourmaline balls, and they're composed of 10% tourmaline shoal, 40% aluminium oxide, 40% borosilicate glass, and a 10% clay binding mixture. So how can these properties be exploited? Well, small-scale lab testing was conducted for the production of alkaline water, and this was a proof of concept. So basically, a circulating test rig to get a fluidized bed with a certain amount of tourmaline ceramic balls of 3.5 millimeters, subjected to a continuous recirculation of water. So small scale, what were the results? Well, started off with a deionized water of pH 7 as a starting point to eliminate any reaction of the OH produced with any water salts which are in tap water. An average of results gave 4 litres of pH 9.5 in 10 minutes using only 24 watts of pump power. And the graph shows the results from different volumes of water recirculation, different weights of ceramic balls, and a consistent fluidization. However, by scaling up the simple test rig to a ship installation, it was estimated that 20 cubic metres of water with pH 9.5 could be generated on board a ship at the cost of less than $25. It's the early stages in the requirements for development of alkaline water scrubbing. At the present time, there are several unknowns as to the practicality of alkaline water scrubbing, and this requires research and development. The following key aspects need to be addressed first. This is for carbon dioxide, but nitrogen oxide may also have to be considered. Is the production of continuous large volumes of water with a pH 9.5 achievable on board a ship? So taking that simple fluidized vessel, can we actually produce or make a larger vessel with much more tourmaline balls inside and have a fluidized bed and produce large quantities of 9.5 water? Secondly, the ratio of carbon dioxide removal to the amount of scrubber water, that's a water of 9.5 pH, is yet to be determined. And the target is 30%. So if we can get 30% reduction in carbon dioxide, how much water of 9.5 does it take? Also, can the carbonate ions in the scrubber effluent water be safely discharged to sea without releasing CO2? Will these ions, combined with excess calcium in seawater, produce stable calcium carbonate? The scrubber discharge has to be greater than 9.5, and that's IMO, and this may have to be controlled by the flow rate of scrubber water or by dilution with additional alkaline water. So there's a lot of work to do and a lot of questions to be answered. So I'd like to summarise what we've gone through, taking the 3 areas from the IMO list of actions. And this is to achieve a minimum of 50% reduction of greenhouse gases by 2050. Efficiency indexes for all ships built after 2025 based on propulsion energy requirements per voyage. And this is based, remember, this is based on the base year of 2008. So index is 30% max. Use of zero low carbon fuels, and it must take into account energy storage. And I've said 30% as a minimum. Perhaps we can actually use more if we have more storage, or we want to incur higher costs for the low carbon fuels. And development and deployment of alkaline water scrubbers, again, circa 30% minimum. So there are caveats to this sort of summary. First of all, the above mix is not cumulative. It's not 30 plus 30 plus 30. The first one is 30% off say 100 units to start off, which gives us 70. The next one is 30% of the 70, which gives us 21, which gives us 49. And the third one is 30% off the 49, which ends up around 34. So the potential for 50% target to be met or bettered. So what's the UK's position on this? Well, the UK government has a plan called the Clean Marine Plan. The UK's route map to clean growth for the maritime sector and the pathway to zero emission shipping. And they have a thing called UK Shore, which is government launches a new unit, UK Shore, to tackle shipping emissions and advance the UK towards a sustainable shipping future. There's 206 million new funding to accelerate research into and development of clean maritime technologies and create skilled jobs across the country. And clean maritime competition, given multi-year extensions for UK organisations to accelerate zero emissions shipping and technologies. So the aim is there, the money is there. Can zero emission shipping or low emission shipping be achieved? So I'd like to finish by thanking you all for listening. Thank you. Goodbye.